In the previous lecture, we talked about vector valued functions. We now have operations involving vector valued functions. Here we say if f and g are two vector valued functions and phi of t to be a scalar function. Both f and g are functions for t. We say f plus g of t, it equals to f of t plus g of t. And f minus g of t is f of t minus g of t. And if you have phi times f of t, it equals to phi of t times f of t. And here, f cross product to g of t, it equals to f of t cross product with g of t. And for scalar function, we say f dot g, it equals to f of t dot g of t. It equals to f of t dot g of t. Now we have an example. In the example, we have given two vector valued functions, which are f of t and g of t. We have given these two vector valued functions, and we should find f plus g of t. We say f plus g of t, as we talked about before in the properties, as you see, it equals to f of t plus g of t. Here, f plus g of t, it equals to f of t plus g of t. And this equals to, here, we just find the sum of the components for f and g. F is t squared I plus t minus 3j plus 3k. Here, we find the sum of the components, component I of f with component I of g, component j of f with component j here. We have no component j in g. That means its component is 0. Then k component with k component here. That means it equals to t squared plus e to the power t times I. As you see, the first component for f and g are t squared and e to the power ti. We've just find the sum of them. Then for j components, for g, its j component is 0 because here you have no j. That means it equals to plus t minus 3j. Then for k component, here you have 3 and here you have t. It's 3 plus t. 3 plus t k. This is f of f plus g of t, which is f of t plus g of t. In finding the sum of two vector valued functions, we just find the corresponding components. Now we have a scalar function which is multiplied by g. We have a scalar function in the second one. We have e of t times g of t. We multiply each component of g by e of t. We multiply each component of g by e of t. It equals to e to the power t times the vector valued function g is e to the power ti plus tk. We multiply both components by e to the power t. We multiply this e to the first and to the second term here. We get e to the power t times e to the power t, which is e to the power 2t. Yeah, we have e to the power t multiplying by e to the power t is e to the power 2ti. Then plus t multiplying by e to the power t is t e to the power tk. This is e of t multiplying by g of t. This is e multiplying by the vector value function g of t. This is the result. Okay, now we have f cross g of t. F cross g of t equals to f of t cross g of t. in the cross product of two vectors, we write down, we can calculate by finding the determinant of this matrix. Here we have I component, J component, and also K component. Then we have f of t. We write down the vector f of t, the first component beneath I, the second component beneath J, and the third component beneath K. Here, the first component in f is t squared. We write down t squared here. And for the second component, which is J, is t minus 3. We just write down the coefficient. And for K component is 3. This is for vector valued function f. Then for the vector valued function g, the component of I, its coefficient is e to the power t. Then for component j, as you see here, you have no component j. That means it's 0. It is 0. Then for K component is t. Now we find the determinant of this matrix. And the result is, we just find the determinant of this matrix. So as you studied the determinant of matrices, I'm just going to write down the result. It is the result is t squared minus 3t times I plus, I'm just going to write down the result, okay? Here, the minus t cubed minus t cubed plus, sorry, minus 3 e to the power t. This is j, then plus this minus, I'm just going to write down the result, okay? It's minus t minus 3 times e to the power t k. This is the cross product of f and g. Okay, now we have dot product of these two vectors. Dot product of these two vectors. Yeah, f dot g of t, it equals to f of t dot g of t. In the multiplication, in the dot product of two vectors, in the dot product of two vectors, we say we multiply each two corresponding components. We say it is, I'm just going to write down the vectors, t squared I plus t minus 3j plus 3k dot product with e to the power ti plus 0j, as you have no j in g, then tk, which is multiply I by I, j by j, and k by k. And in the result, we have no I, j, and k, because here when we multiply I by I times I is 1, j times j is 1, and k times k is 1. Okay, that's why you don't get a vector, you just get a function here in the result. T squared times e to the power t is t squared e to the power t. Then t minus 3 multiplying by 0, that's 0, we don't write down it. Then plus 3 multiplying by t is 3t. This is f dot g. This is the dot product of f and g. These are the result of these questions. We now have the derivative of vector valued function. For the derivative of a vector valued function, we find the derivative of each component. For example, here we have r of t, which equals to f of t I plus g of tj plus h of tk. Here, in finding the derivative of r with respect to t, it equals to the derivative of the first component with respect to t, and the derivative of the second component with respect to t, and the derivative of third component with respect to t. We just find the derivative of each component. Here we have an example. In this example, we are asked to find the derivative of this vector valued function with respect to t. This is the vector valued function. To find the derivative of this vector valued function, we say dr by dt equals to derivative of the first component, derivative of 3t is 3i. 3ti is 3i, because here derivative of 3t is 3. And derivative of sine tj, we find the derivative of sine with cosine, we get plus cosine tj. Then derivative of e to the power tk, its derivative is itself, because derivative of e to the power t is still e to the power t. We get e to the power tk. This is the result. This is the derivative of this vector valued function with respect to t. We just find the derivative of each component. We now have higher degree derivatives of vector valued functions. For finding second, third, and so on, and for nth derivative for a vector valued function, we find the nth derivative of each component. Okay, for example, for the second derivative, we find the second derivative for the first component, the second derivative for the second component, and the second derivative for the third component. And for triple derivatives or third derivative, it's the same. Now we have this example. In this example, we are asked to find the second and third derivative. We should find the second and third derivative for this vector valued function. To get the second derivative, we must first find the first derivative and then the second derivative. Okay, and then from the second derivative, by taking its derivative, we get third derivative. Here we say r prime of t, which is the first derivative, it equals to derivative of each component here. The first component is 3ti. Derivative of 3t is 3i plus derivative of sine j, sine tj. Derivative of sine is cosine. Then e to the power tk, its derivative is e to the power tk. This is the first derivative. For the second derivative, which is r double prime of t, it equals to, we take the derivative for the first derivative to get the second derivative. Okay, now we have 3i. Derivative of 3i is 0i, which is 0. Okay, we get 0i because derivative of 3 is 0. It's a constant. So we have no I component in r double prime. Then for derivative of cosine, derivative of cosine is minus sine tj. Then e to the power t, its derivative is itself k. That's the second derivative. Then for the third derivative, r triple prime of t equals to derivative of sine is cosine, and here we have a negative sign also. We get minus cosine tj plus a to the power t k. This is the third derivative, and this is the second derivative. As you see, this is the first derivative. It is the answer for this example, as it's asked to find the second and third derivative for this vector valued function. Now we have differentiation rules for vector valued functions. We say the derivative of a constant multiplying by a vector, it is c, which is the constant, multiplying by the derivative of the vector. Okay, and a derivative of f times u, f times u. It's first times derivative of the second plus second times derivative of the first. Okay, here we have f and u, f and u. F is a scalar function and u is a vector valued function. Here we see the multiplication of a scalar function with a vector valued function. It's the derivative of the dot product is first times derivative of the second plus second times derivative of the first. It's the same rule as we studied before. And here the derivative of the sum or subtract of two vector valued functions is the sum of the derivatives, or the sum of the their difference. And here we say the derivative of the dot product of two vectors. The dot product of two vectors, two vector valued functions, is derivative of the first times second plus first times derivative of the second. It's the same. Here we have the derivative of cross product of two vector valued functions. It equals to derivative of the first vector valued function, then cross product to the second vector valued function, then plus first vector valued function cross product with the derivative of the second vector valued function. These rules are similar to the rules that you studied before in finding the derivative of functions. Here we have this rule also. We say if r is differentiable at t, and t is differentiable function of s. Here we say r is a function of t, and t is a function of s. Then if we want to find the derivative of r with respect to s, in this case, we must use a chain rule. We must use chain rule for finding the derivative of r with respect to s, because in r we have t. We have t as the variable, but t is a function of s. Here we say dr by ds is dr by dt times dot product with dt by ds. We say dr by ds, it equals to dr by dt dot product with dt by ds. This is the chain rule in vector for vector valued function. Now we have integrating vector valued function. We say the integration of a vector valued function is the integration of each component. It's the same as the derivative. In the derivative, we said we just find the derivative of each component, and here we say we find the integration of each component. As you see here, the integration of r of t. In r of t, you have f of t, g of t, and h of t. We find the integration of each component, and we write down the components I, j, and k. We say if we have a constant multiplied by a vector valued function, its integration is equal to the integration of the vector valued function and then multiplied by the constant. For the sum or subtract of two vector valued functions, if we find their integration, I mean the integration of the sum of two vector valued function or difference of two vector valued functions is the sum or difference the integrations. Is the sum or difference of their integrations. We can give the integration for each vector valued function. And here you say the derivative of integration for r of t, the derivative with integration are cancelled out, and you get only r of t. You get only r of t. But here we say the integration of derivative of r of t, if we have integration then derivative, it's different from derivative and integration. We say this equals to r of t plus c. We just add c for the result. We just add c for r of t. Okay, here derivative and integration are going to cancel out, and here we get c as the constant of the integration. Now we have tangent vector. we say let R of t to be f of ti plus g of tj plus h of tk. This is a vector valued function of a curve in xyz plane. We say add t to be t naught, add t to be t naught. That means if we replace each t by t naught, if you are given a point, we say R of t naught is the position vector. And this vector is called a position vector. It's called the position vector. That means if we replace each t by t naught is a point. Okay, we get the position vector. And the first derivative of R of t at the point, as you see, that's it. This is the first derivative of the vector valued function. And then we replace each t by t naught in the first derivative. We say this derivative is called tangent vector. This is the tangent vector. Okay. Here we say R of t naught is the position vector, but R prime of t naught is the tangent vector. Okay, this is the tangent vector. As you see here, you have an example. It says sketch the graph of R of t and its position vector and tangent vector at t to be t1. And here we are going to find first we sketch the graph, then we are going to find the position vector, which is R of t naught. Here t naught is 1. Here t naught is 1. R of 1 is the position vector. Then the tangent vector, we find R prime of 1. This is the tangent vector. Okay. In the example, we should find three things. First, we sketch the graph. Then we find the position vector. And finally, we find the tangent vector. For sketching the graph, we make a table for t, x, and y. We let x to be t squared. Here, we say it's xi plus yj. Here, the first component we replaced by x. It means x equals t squared and y equals t. Here we make a table for t, x, and y, and then for xy. We give values to t. We find x and y. Okay. Let t to be -2, t to be -1, t to be 0, t to be 1, and t to be 2. Now we find x and y. If t to be -2, x is t squared. That means x is 4. And y is t, which is -2. Then xy is 4 and -2. This is the first point. And the second point is -1. T is -1. X is 1 because x is t squared. And y is t, which is -1. That means it is 1 and -1. 0. X is t squared, which is 0. And y is t, which is still 0. Then it's 0, 0. And if t to be 1, x is t squared and y is t. That means it's 1 and 1. It's 1, 1. Then if t to be 2, x is 4, y is 2. So the point is 2 and 4. Now we plot these points on the xy plane. Let's plot them on the xy plane. Let's say this is 1, 2, 3, 4. So the points are this x and that's y axis. 4 and -2. It's 1, 2, 3, 4. This is 4 and -2, which is somewhere here. This is 4 and -2. And also negative 1 and negative 1. The second point is 1 and negative 1, 1 and negative 1, then 0 0, and then 1 1, and then 4 and 2. We join these points and we get the graph. This is the graph of the vector valued function. This is the graph of the vector valued function. Let's answer for the first part of the question. In the second part, we should find the position vector. We said the position vector, as you see here, we said r of t naught, r of t naught is the position vector. Here we have given the position vector. The position vector is, we have given the value of t naught, which is 1. Now the position vector, which is r of 1, this is the position vector. Position vector is r of 1, since you have given r is 1, which is r naught, which is t naught, sorry. R of 1 equals 1 squared I, what's 1I, plus 2 times tj, which is 2 times 1 is 2j. So it equals to I plus 2j. This is the position vector. This is the position vector. Then for the for the third part of the question, it's tangent vector. We say tangent vector is r prime of t naught. That means r prime of 1. We first should find r prime. We should first find r prime. R of t is t squared I plus 2tj. We find the derivative of each component. We say r prime of t is 2t plus 2ti, sorry, 2ti plus 2tj. Its derivative is 2j. Then r prime of 1, r prime of 1, which is the tangent vector, equals to, we replace each t by 1. We get 2 times 1 is 2, it's 2i plus 2j. This is the tangent vector. So this is the answer for this example. We now have, before we go on to the next page, we have this note here. I forgot to talk about this note. We say the vector position r of t naught and the tangent vector r prime of t naught doesn't have to be orthogonal to each other. Okay, doesn't have to be orthogonal to each other. That means they are not perpendicular to each other. We say equation of a tangent line on the curve of a vector valued function r equals to r of t, t to be t naught equals to, this is equation of the tangent vector. Equation of the tangent vector. It equals to, we say the equation of the tangent vector equals r of t naught plus t times r prime of t naught. We say it's r of t naught plus t multiplying by r prime of t naught. So for finding the equation of a tangent vector, what we do, we should find r of t naught, then we should find r prime of t naught, then we find the sum of these two and we multiply this by t. Okay, so the equation of the tangent vector is r of t equals to r of t naught plus t times r prime of t naught. That means we find r of t naught and r prime of t naught. Then we find the sum of r of t naught plus t multiplying by r prime of t naught. Here we have given an example. This here r prime t naught is the tangent vector, but the equation of the tangent vector is different from the tangent vector. Here r of t naught is the position vector, so here we must find the position vector and the tangent vector. Then we find the sum of the position vector and t multiplying by the tangent vector. Here we have given an example. In the example, we have given the vector valued function. We have given vector valued function. We should find the equation of the tangent line. Equation of the tangent line. Equation of the tangent line is the position vector plus t multiplying by the tangent vector. Okay. It says find at t equals 2. That means here t naught is 2. T naught is 2. Now we find, first let's write down the equation of the tangent line. We say r of t equals this equation of the tangent line. It equals to r prime of t naught plus t multiplying by, sorry, r of t naught, not r prime. R of t naught plus t multiplying by r prime of t naught. So we must find r of t naught and r prime of t naught. First, let's find them. We say r of t naught equals, here t naught is given, which is 2. It equals to r prime of 2, and r of t naught is r of 2. We find these two. That means in the vector valued function, we replace t by 2 for finding r of t naught, and we find the derivative. Then we replace t by 2 for finding the r prime of t naught. Now let's find them both. R of t naught equals r of t naught. We replace each t by 2 in the given vector valued function. That's 2ti. If we replace t by 2, we get 4i. Then plus t squared j. If we replace t by 2, we get 2 squared, which is 4j. Then t times k, which is 2k. This is r of t naught, which is r of 2. Okay? This is r of 2. Then we should find r prime first here. R prime of t equals, we find the derivative of each component. Derivative of 2ti is 2i plus derivative of t squared j is 2tj. Derivative of tk is only k. Now, to find r prime of 2, we replace each t by 2. We get 2i plus 4j plus k. Now, to find the equation of the tangent line, r of t equals r of 2 plus t multiplying by r prime of 2. We multiply r prime of 2 by t, then plus r of 2. So r of 2 is 4i plus 4j plus 2k. This is r of t naught, sorry, which is 2. Then plus t multiplying by r prime of 2. R prime of 2 is 2i plus 4j plus k. If we multiply this factor by t, we get 2ti plus 4tj plus tk. Now we find the sum of these two vectors. It's the sum of all the corresponding components, which is 4i plus 2ti. It's 4 plus 2ti, then plus 4j plus 4tj is 4 plus 4tj, and 2k plus tk is 2 plus tk. This is the equation of the tangent line. This is equation of the tangent line. So this is the answer for this example. Now you have orthogonal theorem of a vector valued function. We say if a vector valued function r of t is not zero, if it's not zero, is differentiable and its magnitude is a constant. Here we say if the magnitude is a constant, if the magnitude of a vector valued function is a constant, that means the norm of t, the magnitude of r of t is k. Then r of t and r prime of t are orthogonal. At this case, we say these the vector valued function with its derivative are orthogonal. But if the magnitude is not constant, it may not they may not be perpendicular or orthogonal. Okay, so in this case, if the magnitude of a vector valued function is a constant, then the vector valued function, then the vector with its derivative are perpendicular. Yeah, that means r of t dot product with r prime of t is 0. We say if the dot product of two vectors is 0, it means these two vectors are orthogonal. These two vectors are orthogonal. Here, the dot product of two vectors, for example, here r and r prime, that equals to the the magnitude of r multiplying by magnitude of r prime times, this is cosine, this is c, cosine theta multiplying by cosine theta. This theta is the angle between r and r prime, and you also can find this in another way. We say it is we multiply the components, the corresponding components. If we have, let's say, if r to be ai plus bj plus ck, and r prime is, let's say, di plus ej plus gk, then the dot product of these two, r dot r prime, equals to a times d plus, here we have no I, j, and k in the dot product of two vectors. We just get a value or a function. It's ad plus be plus cg. As you see, we just multiply the corresponding components and then we find the sum of them. Here we have given an example. In the example, it says, is r of t and r prime of t orthogonal? For these vectors, here for the first one, for a, we find the dot product of r and r prime, r prime. If the result is 0, we say they are orthogonal. If the result is not 0, we say they are not orthogonal. Here, r of t equals t squared I plus 2tj. And r prime of t is, we find the derivative of each component, which is 2ti plus 2j. Now we find the dot product of R with R prime. You see R of T dot R prime of T. It equals to, we multiply the corresponding components, T squared multiplying by 2T, which is 2T cubed, plus 2T multiplying by 2, which is 4T. This doesn't equal to 0. That means R and R prime are not orthogonal. For the first example, we say they are not orthogonal. For the second one, we have R of T, which is sine T I plus cosine Tj. For B, R of T is sine T I plus cosine T J. We find R prime of T equals derivative of sine is cosine Ti plus derivative of cosine is negative sine, which is minus sine Tj. Now we find R of T dot R prime of T and we find the result. R of T dot R prime of T, we multiply sine by cosine, sine T and cosine T plus cosine T by negative sine T times negative cosine T. So it's negative sine T. And the result is sine T cosine T minus sine T cosine T. The result is 0. We see R and R of T and R prime of T, R of T and R prime of T are orthogonal. Why? Because their dot product is 0. Here, for showing that two vectors are orthogonal, we say we will find the dot product of the vectors. If the result is 0, we say they are orthogonal. If the result is not 0, we say they are not orthogonal. We now have unit tangent vector. For the unit tangent vector, we say a unit tangent vector is a vector with magnitude 1. That means if the magnitude of a vector is 1, we say that vector is a unit vector. Okay? It's a unit vector. We say the unit vector U, which is parallel to the vector this one. To find the unit vector which is parallel to a vector, a given vector. To find U, what we do? We divide V by its magnitude. We divide V by its magnitude. As you see here, we have given this example. It says find the unit vector which is parallel to this vector. Here, to find the unit vector, we say U equals V dividing by its magnitude. So you should first find the magnitude of V. I'm going to solve it here. The magnitude of V is the square root of squaring the sum of squaring all components as 3 squared plus 2 squared plus 1 squared. 3 squared is 9 plus 2 squared is 4 is 13 plus 1 squared, which is 1, is the square root of 14. This is the magnitude of V. And now we say U equals V over the magnitude of V, which is V is 3I plus 2J plus K, dividing by the square root of 14. And this equals to, we divide each component by the square root. It is 3I over 4 square root of 14 plus 2J dividing by square root of 14 plus K dividing by square root of 14. This is the unit vector. This is the unit vector which is parallel to V. It's how to find a unit vector. Now, if you want to find the magnitude of U, if you want to find the magnitude of U, it must be 1. Let's see. The magnitude of U is just for satisfying the results, okay, is 3I over square root of 14, which is 3 over square root of 14 squared plus 2 over square root of 14 squared plus 1 over square root of 14 squared. And here this equals to 9 over 14 plus 4 over 14 plus 1 over 14. And this equals to square root of 14 over 14, which is 1. As you see, its magnitude is 1. Okay, so U is a unit vector and its magnitude must be 1. And the unit tangent vector, U, I mean the above one, is the unit vector. But the unit tangent vector, it's denoted by T of T. It's denoted by T of T. It's a unit vector that's parallel to the tangent vector R prime of T. That means we are going to find the unit vector which is parallel to R prime of T. Okay. Here, if you have given a vector, to find the unit tangent vector, we must find the derivative of the vector first. Then we find the unit vector for the derivative. That means T of T is R prime of T dividing by its magnitude. We have given an example. In this example, it says find the unit tangent vector. We should now, as we have unit tangent vector, we must find R prime of T dividing by norm or the magnitude of R of T, R prime of T. We must find R prime of T dividing by its magnitude. But here in the example, we have given R of T. So you must first find the derivative of R of T. Then we find T of T, which is the unit tangent vector. And it says find it where T is 1, where T is 1. So first, let's find R prime of T. We say R prime of T, I'm just going to write down here, R prime of T is 2Ti plus 2J. And R prime of 1, as we have given it, is 2 times 1 is 2, 2I plus 2J. We are going to find the unit tangent vector from this vector. Now we see the unit tangent vector T of T is R prime of T divided by R prime of T at T naught, at T naught. Here we have given T naught. If we have not given T naught, we just use this one. But here we have given T naught, so that's why we must find R prime of 1. Then we find it. So t of 1 equals r prime of 1 dividing by the magnitude of r prime of 1. And this equals to, first let's find the magnitude. We say the magnitude of r prime of 1 equals the square root of first component square plus second component square, which is 4 plus 4, which is square root of 8. This square root of 8. This is the magnitude of r prime of 1. We divide r prime of 1 by the magnitude, which is 2i plus 2j, and here the magnitude is, we can say it's 2 square root of 2, because it's 4 times 2. We take 4 out of the square and it becomes 2, which is 2 square root of 2. And here it's 2i plus 2j dividing by 2 square root of 2. We divide each component by 2 square root of 2. If we divide 2i by 2 square root of 2, these two are cancelled out and we get I over square root of 2 plus j square root of 2. Because these two here, it becomes 2i over 2 square root of 2. These two are cancelled and you get only I over square root of 2. And for j, it's the same. So this is the unit tangent vector at t to be 1, at t equals 1. But if we have no given this one, you find it from this one, this vector. You find its magnitude and also divide the vector by its magnitude, and you get the results. Here we have principle of normal unit vector. Here we talk about normal unit vector. Let's see how to find the normal unit vector. In the previous slide, we talked about unit tangent vector, and we said the unit tangent vector could be obtained from a vector valued function. Okay, and since it is unit tangent vector, since that's unit vector or unit tangent vector, that means it is magnitude is 1. So the magnitude of the unit tangent vector must be 1. As you see, it is a constant. Then, according to the theorem of orthogonal, or the orthogonal theorem, we said in the theorem, we said that if the magnitude of a vector is a constant, then it is orthogonal with its derivative. Here, t of t, we have t of t, which is the unit tangent vector. Its magnitude is 1, which is a constant. That means t of t must be orthogonal with its derivative. That means here t of t and t prime of t must orthogonal. Why? Because the magnitude of t is 1. It's a constant. We say the normal unit vector is t prime of t dividing by the magnitude of t prime of t. Here we find t of t, then we find t prime of t. After finding t prime of t, we find its magnitude, then we divide t prime of t by its magnitude, and we get the normal unit vector. Here we have given an example. In this example, it says find t of 1 and n of 1. But here we have given a vector valued function. Look, from the vector valued function, we can find t of 1. And then we can find t of t. Then from t of t, we can find the normal unit vector, which is n of t. Here we say t of t is r prime of t dividing by the magnitude of r prime of t. So here we have given r of t. We first must find r prime of t. So r prime of t is 2ti plus 2j. Then we say find t of t. To find t of t is r prime of t dividing by it is magnitude. So r prime of t, let's find its magnitude first. We see the magnitude of r prime of t is the squaring of all components, which 2t squared is 4t squared plus 4. This is the magnitude. Then t of t is r prime of t, which is 2ti plus 2j dividing by the magnitude. The magnitude is the square root of 4t squared plus 4. Okay. Now, to find the unit tangent vector, it is 2t dividing by the square root of 4t squared plus 4. This is I plus 2 over square root of 4t squared plus 4j. This is t of t. How about t of 1? We just replace each t by 1. We just replace each t by 1. And from this, we can say t of 1 is, we replace each t by 1. And we get 2 over. If we replace t by 1, we get 2 square root of 2, which is square root of 8. We get square root of 8 in the denominator, which is 2 square root of 2. This is I. These two I cancel out. Plus 2 over 2 square root of 2j. These two are cancelled out. So we get 1 over square root of 2 here and 1 over square root of 2 here. This is the unit tangent vector at t to be 1. This is capital T of 1. Now, to find n of 1, we must first find n of t, then we replace each t by 1. But here we have the rule for finding n of t. We say it is derivative of the unit tangent vector dividing by its the magnitude of the derivative. Let's find t prime of t first. T prime of t here we can get from this. You find the derivative of each component. So the derivative is it equals to 8 over 4t squared plus 4 over to the power 3 over 2 I. Here I'm just gonna write down the result. It's here we apply the quotient rule of derivative, which is denominator squared, then denominator times derivative of the numerator minus numerator times derivative of the denominator, then plus here we get minus 8t dividing by 4t squared plus 4 to the power 3 over 2. This is j. This is t prime of t. Now we find the magnitude of this vector. So the magnitude t prime of t find the square root of squaring of each component. The first component is, if we square this, it becomes 64 dividing by 4t squared plus 4 to the power 3. Then plus the second component becomes minus 8t over 4t squared plus 4 to the power 3 over 2. If we square this, we get 64t squared over 4t squared plus 4 to the power 3. And this equals to the square root of 64 plus 64t squared dividing by 40 squared, as both have the same denominator. That's why you just find the numerators as 40 squared plus 4 to the power 3. This is the magnitude. Now we divide t of t by its magnitude, and we get n of t equals t prime of t by its magnitude, t prime of t. So here we divide each component of t of t, t prime of t, by this magnitude. Or we can say, we find, to be easier, we find t prime of 1, and then we divide it by t prime of 1, I mean its magnitude. The magnitude of t prime of 1. Now let's find t prime of 1 and the magnitude of t prime of 1. So t prime of 1 from this, t prime of 1 equals, we replace each t by 1. And here we get 8 cubed in a square root. 8 dividing by, if we replace t by 1 here, we get 1. 4 plus 4 is 8. 8 to the power 3 over 2. This is I plus. The second one becomes minus, sorry, it's minus. If we replace t by 1 here, we get a minus 8 over the same, 8 to the power 3 over 2. And 8 to the power 3 over 2, it's the same as to say 8 in a square root to the power 3. Or you can say it is 8 to the power 3 in a square root. Okay, this equals to 64 times 8, which is 8 square root of 8. That means it is 8 square root of 8. So the magnitude of t prime is, sorry, the denominator of t prime of 1 is, this is 8 square root of 8. And this also. This is 8 square root of 8. These are cancelled out, and these also. And you get 1 over square root of 8. And here also 1 over square root of 8. This is t prime of 1. Now, from this, the magnitude of t prime of 1 equals, let me write down below here. From this, the magnitude of t prime of 1, we can replace each t by 1 here. In the numerator, in the square root, in the numerator, we get 128, because 64 plus 64 is 128. And in the denominator, we have 8 cubed, which is 512. Okay, it is 512. And this equals to the square root of 1 over 4. Yeah, dividing by 128 is 4. This dividing by 120 is 1. Okay, which is this 1 over sorry, it's 1 over 2. It is a half. So this is the magnitude of t prime of t, and this equals to 1 over square root of 8i minus 1 over square root of 8j, all dividing by a half, and this equals to 2 over square root of 8i minus 2 over square root of 8j. And square root of 8 could be written as 2 square root of 2, because it's square root of 8 is 4 times 2. So 4 could be checked out with the square, it becomes 2. So we get here 2 square root of 2. And here also we get 2 square root of 2. These are cancelled out, and this becomes 1 and 1. So this is the normal unit vector at 1. This is n of 1. Let's write down n of 1, which is t prime of 1 dividing by the magnitude of t prime of 1. This is the result. This is the normal unit vector at 1, and this is the tangent unit vector. Okay, yeah, it's so easy. It's just following the rules. That's so easy. Now we have object's motion on a curve. Say an object moves on a curve in xyz space, given by vector valued function r of t is x of ti plus y of tj plus z of tk. So the trace or path of moving object at any time t to be t naught is given by the position vector. So if we are asked to find the trace or path of the object of the moving object is r of t naught. Okay, for example, if you are asked to find the trace of a moving object at second 3, for example, minute 4. Okay, here we say we just replace t by 4 or 3 or any time that you are given in the example in the vector valued function r of t. We just replace t by the given time. Then we get the position vector, which is the trace or path. Then for the velocity of the vector at t to be t naught, we find v of t naught, but the velocity is the derivative of the position vector. Derivative of the vector r, we find r prime at t naught. So the velocity at time t naught is the derivative of the the vector value function r of t. Then we replace t by t naught. We find its derivative, then we replace it by t naught. And the speed is the magnitude of the velocity. The magnitude of the velocity is speed. And the direction of the moving object, at t to be t naught is the unit vector, of the velocity. Is the unit vector of the velocity at t to be t naught. Here we find v of t naught. Then we find its the unit vector which is parallel to the velocity, which is the velocity vector at t naught dividing by its magnitude. We just find the unit vector which is parallel to the unit vector, to the velocity vector. Then for acceleration is the derivative of the velocity. Is the derivative of the velocity. Okay. Here we find the derivative of the velocity. We get the acceleration, or we can find from the vector r by taking its double derivative. Here we have given two examples. In the first example, it says find the velocity and the acceleration vectors of an object moving on a path given by this. This is the vector valued function, which is which denotes the path function. Okay, at 1, 1, 1. So what's the speed of this object here? Here we should find the speed of the object. We say the speed of the object is the magnitude of the velocity at that point. At that point here, x is 1, y is 1, and z is 1. But we also have given that x is t, y is t squared, z is t cubed. That means t equals 1. T equals 1. Okay, t equals 1. That means here, at time to be 1, we find the speed of the object. So in the case, if you have given that at the point, if the point to be 2, 4, and 8, for the same example. Here, we say x is 2, y is 4, and z is 8. Here, for the components of the given vector, we say x is t, y is t squared, and z is t cubed. Here, we say x is t equals 2 also. That means t equals to 2. And from y, we can say t squared equals 4. That means t is 2. And t cubed is 8 from z, which is t is 2. Okay. Here in this example, we are given that x is 1, y is 1, and z is 1. Since x is 1 and x is also equal to t, that means t equals 1. Okay. So here we find the speed at t to be 1. We say speed equals the magnitude of the velocity at t naught. And here t naught is 1. T naught is 1. Let's solve this. Here, for example A, we say t equals 1, or t naught equals 1. The speed is the magnitude of the velocity at 1. First, let's find the velocity. We say the velocity is the derivative of the path function or the trace function. We find the derivative of the path function. This is the path function. We find the derivative of this, in the path vector. We find the derivative of this vector to get the velocity. We say v of t equals r prime of t, which is, you find the derivative of r, which is I plus 2tj plus 3t squared k. This is v of t. Now we find v of 1. Then we find the magnitude of v of 1, because it says find the speed at that time at 1, 1, 1, and we found that t is 1 at time to be 1. Here v of 1 equals, we replace each t by 1, we get I plus 2j plus 3k. If you replace t by 1, we get this vector. Now we say speed equals the magnitude of v1, which equals to the square root of 1 squared plus 2 squared plus 3 squared, which is square root of 14. This is the speed. So the speed of that object at t to be 1 is square root of 14. Square root of 14. This is the speed. And then for example 2, it says find the position vector r of t. if the velocity vector is this vector, and the position vector at t to be 0, here we have given t, which is 0, at time 0, is r of 0, which is I plus 4j minus k. This is the position vector. As you see here, we should find the position vector r of t. We should find the position vector r of t from the velocity. But we have given this condition. This is the condition. We use this for finding the constants that we get from the integrations. As you see, we say v of t equals r prime of t. How about r of t? R of t is the integration of v of t. Is it? Here, we say v of t, velocity, is the derivative of the position vector. Is the velocity of the derivative of the position vector, and the position vector is the integration of the velocity vector. Now we have given the velocity vector. Now we should find the integration for the velocity vector, and we apply this condition. We apply this condition, which is r of 0, to find the constants that you get from the integration. First, let's write down the equation of the velocity. We say v of t, v of t equals t squared I minus e to the power 2t j plus square root of t k. Okay, we should find r of t. We say r of t equals the integration of v of t dt, and this equals to the integration of each component, the integration of t squared dt I plus minus integration of e to the power 2t dt j plus the integration of square root of t dt k. Now we find these integrations. In taking this integration, we get a constant from each integration. We get a constant from each integration. We say it equals to, that means r of t equals, this equals integration of t squared is t cubed over 3. T cubed over 3 plus, let's say, a. This is the constant that we get from this integration, this I, minus integration of e to the power 2t. You must have the derivative of the exponent, and the derivative of the exponent is 2. And here we have a half also. We say it is a half of e to the power 2t plus, let's say, b. We get a constant here also, j. Then plus integration of t in a square root. That's integration of t to the power half. Integration of this function with respect to, we just add 1 for the exponent and dividing by the new exponent, which is t to the power 3 over 2 dividing by 3 over 2, and becomes 2 over 3. Okay, we get 2 over 3 t to the power 3 over 2 k. So it's plus a constant, let's say plus c. Now this is r of t, but here we must find the values of these constants. We have given that r of 0 equals I plus 4j minus k. That means if we replace t by 0 here, these two, this vector must equal to this one after replacing t by 0. Let's see. Here, r of 0 equals, we replace t by 0. Here we get ai minus if we replace t by 0 here, we get minus a half 1 plus b j plus 2/3 c. This becomes 0 and this becomes 0. K. This equals to what? Equals to that given vector r of t naught, r of naught, r of 0, sorry. I plus 4j plus k minus k. R, sorry, I plus 4j minus k. Let me check. Yeah. Now we equal each two components. Since these two vectors are equal, so all the corresponding components must equal. That means ai equals I. That means here a is 1. A equals 1. And here minus a half times 1 plus b equals 4 minus a half times 1 plus b equals 4. We equal this component to the coefficient of j. And here we can say b equals, it is minus, it's minus 8 minus 1 is minus 9. B is minus 9. We found this. And 2/3 of c equals negative 1. 2/3 of c, let me write down there. 2/3 of c equals negative 1, because here the coefficient of k is negative 1 and the coefficient of k here is 2/3. And so c is minus 3 over 2. This is c. We found these three. Now we return them into the r of t. And it says find the positive vector at t to be 0. So we say r of 0 equals, r of 0 equals, we replace each t by 0 for this one, and we replace b by minus 9, a by 1, and c by minus 3 over 2. Okay, we get I minus a half 1 plus minus 9 is minus 8. So this becomes positive. It is, so the result, I'm just going to write down the result. If you replace b by negative 9 and you replace t by 1, we get minus 8 in the bracket. And in the out of the bracket, we have minus a half. Minus times minus becomes positive. And 4, 8, and 2 are cancelled out, and we get plus 4j I plus 4j minus, here we replace c by minus 3 over 2, and here we have 2/3. If we replace t by 0 here, we get that it is minus k. As you see, we got the same as we have given here, and also we must go the same. We must go the same. Okay, but for finding r of t, it's just for satisfying it. For finding r of t, we just replace, yeah, we replace each a, b, and c by their values. We get r of t. We are asked to find r of t. Okay, r of t is t cubed over 3 plus a is 1, I minus a half e to the power t, b is negative 9, j plus 2/3 t to the power 3 over 2, c is minus 3 over 2. Okay, this is the position vector. This is the position vector if the velocity vector is this one. And we have given this condition. Look, this condition is given for only finding the values of constants. We found the values of constants from this given conditional vector. That's enough for today.